Now we are going to implement the same convolution neural network using Tensorflow. We are not going to use Keras framework anymore. So here I have created a new notebook. So I'm going to give a good name to it. Let's name it okay. So first we are going to import the required modules and packages. This is Markdown cell. Okay, we are going to import Tensorflow, and along with that we are going to use pointers to handle some of the data frame, and NumPy and Matplotlib libraries. So let's import them. It may take some time to import, but you can wait for it. So in the next step, we are going to import the data set. We are going to use MNIST data set. So let's start our data import. Let me rename this cell. Saving it in data variable. I'm going to do so let's import it first. I have not imported it yet. It may take some time, so in the meantime I'm typing the next data load step. I'm saving it in the variable data. MNIST input data. I'm going to read. They have made it very easy for us. You have to specify the directory where the NumPy file should be downloaded. And we're going to have the labels as in one hot mode, so we have to specify another argument here, that is one hot. Yes, that is one hot. Okay, it may take some time if you are doing it for first time. Next step, we are going to define the hyperparameter. The TensorFlow code would be a little bit of longer and big, and if you don't keep the variables declarations clear enough, you will miss a few of them, and it may be a little bit of chaotic. So considering that thing, all the hyperparameters, I'm putting everything together in this particular cell. So let's give a name to this particular cell. What comment we should use? Let's define that parameter. All right. So first we are going to specify the learning rate. So I'm using default learning rate as 0.1. Next, I'm going to use the batch size. Let's start with 128 and number of epoch. Let's specify. Let's specify one as of now. Later we can change it once our code has started executing. In our model, we are going to have two initial convolution layers, two max pool layers, then two or one dense layer, and then one output layer. So first, let's specify the parameters for convolution layer. Conv1 equal to, let's have a total 16 filter for the first convolution layer, and the kernel size it's a 3 by 3 filter size. Let me take it a little bit of off what I'm doing. Okay. Okay. Next, second convolution layer, conv2, we are going to have 32 filters and key size 2 equal to 3. Now we are going to have the max pool size. We are going to use a pool size of 2. That means it is going to take the max value from a 2 by 2 patch and it is going to shift 2 cells to the right and bottom. We are going to have a dropout as well. Let's define it. I'm not sure the let's define that dropout as well. Let's define the dropout for convolution as 0.5 and dropout for dense equal to 0.5. Both of them are same. Let's give a full name. Now it's the time for dense layer. Let's have 64 neurons in the dense layer, and for the output layers, we'll have 10 neurons as output for each and every digits between 0 and 9. This is not a hyperparameter, but let's define the initializer as well. Basically weights and bias initializers. In this particular case, we are going to initialize only weights using that Glorot uniform initializer. It's in contribution layers. All right, save here. Okay, so this is our initializer. Let's define this. Okay, next step, we are going to define the required functions, different kind of layers basically, and first we are going to create dense layer, the easiest of everyone. Define dense layer. Okay, X is the input, W is the ways, and P is the biases. Okay, so this is the net input, and we are going to use alright, so let's do it. Matrix multiplications. We are going to have multiplications of X and W. Then we are going to have we'll add the biases with it. So this is the net input. Now we are going to use ReLU activation function by default to all these dense layers. So let's define the activation output. It should be part of neural network ReLU. Okay, it's going to take the input as net input, and it is going to return the activation output. So our dense network definition is done. Now we are going to define convolution layer. This is the 2D. I'm going to keep it very similar to Keras function. It is going to take input as X, W, B, and one more thing, like the stride length, we can pass it stride equal to 1. Here I am setting up the default stride length equal to 1. So you can play with it, you can make it 2, 3, 4, whatever you want later. We have to do it in a different way, like we cannot add a simple way like whatever we did with the net input plus the biases. Step equal to dot Tensorflow has a 2D convolution function which is going to take X, W, weights, biases, and strides equal to, I hope that was strides. Okay, it is strides. Now for each image we are going to have strides of whatever values you are passing toward X directions, Y directions, and for each channel. And along with that, we have to specify the padding as well. Here we are going to use same. That means it is going to generate the same size image after applying the filters. So next what we are going to do, we are going to calculate the net input equal to TF neural network add it should be bias add. Okay, yeah, this is the function. This is specially designed to handle the bias additions for convolution type of network. So what it is going to take, it is going to take X, W, whatever we have calculated, and it is going to add those things with B. Now we are going to use the ReLU activation function as well. ReLU, let's apply it to the C, and it is going to return A. third type of layer which we are going to create, that is max pool layer. Max pooling 2D, similar to whatever we have for convolution. Okay, it is going to take input as X, and it will not record any kind of bias and weights, but it will record the pool size. We are going to use same pool size and stride in this particular case, so we are passing only one values. Equal to max pool 2D. We are going to use the default function as max pool from Tensorflow neural network library, and we are going to pass the same values, and the kernel size will be similar to the stride whatever we have specified above. For each input, the size is the kind of pass size is the pool size whatever we are specifying for each channel, and stride should be the same. So I'm going to copy this content. Okay, this is simple. Okay, I'm going to use the same padding here. It is going to return A. And two more type of layers you will require. Those are kind of flatten layer and reshape layer. Reshape is not layer basically. That we are going to handle it dynamically during our network creations. So let's keep that thing inline itself. Alright, so another important thing here we have missed is we have to define the weights and biases, and we have to initialize them. So let's create the weights and bias dictionaries. Basically, let's create the variable required for this network. First type of variables would be X and Y, which are basically placeholder from TensorFlow term point of view, and that means we are going to provide the values for X and Y dynamically during our executions. So let's create a placeholder for X and Y. It's equal to DL dot placeholder. It is going to be a float, 30 decimal float point, and it will have dynamic number of records, and each of them will have size of 784. Alright, so one important thing here is that the data set which we are importing from TensorFlow example libraries for MNIST data, it is already flattened. So that means we are going to have an array which will have a total 784 records, 784 digits. So that's why the input shape is basically each and every input contains single line, one row, and 784 columns. So that's why I'm defining it like this. Okay, y equal to placeholder same float 32, and it is going to have number of okay, so it is going to have 10 columns. We can use the variables whatever we have defined here, but still that should be fine. Okay, so placeholders are created. Now we have to create the weights and biases. So It's a good practice to create the weights and biases in a form of dictionary so that you can maintain everything together. So that is exactly what we're going to do here. I'm going to create two dictionaries. Let's define the first easy one, bias dictionary, and it is going to have biases for the first convolution layer, and it is going to be a variable type, and the size of in conv1. Okay, so I'm creating the variables biases with the 0 initial values, so that's why I'm just creating those many number of zeros with the exact size of the convolution neurons, number of convolution neurons in the first layer. So this is pretty much the syntax to create a 0 value variables. I'm going to create the second one. I'm going to give a different name to it. Okay. It will have this value whatever we have, convolution in conv2 1 2. Okay, so BC2. Third, we are going to have for dense layer. Alright, so this is what the first dense layer, and alright, and the next one would be for output layer. Out df dot variables df dot zeros classes. Okay, the biases are created, I believe. Okay, next one we are going to create the weights. Alright, so we'll have similar name like W convolution 1, and this is what we are not initialize it as 0. We are going to use the Glorot uniform initializer, whatever we have defined here. So to do that thing, we need to get the variables. Get variables, and we have to define the data type. Data type equal to Tensorflow float 32. We're going to give a good name to it so that it can be shared with the multiple devices later in extreme programming mode. It is going to have, we have to define the shape as well. Shape equal to, now this is what we will have the kernel size. Okay, where is my, okay, so 3 by 3, and this is input channel and this is the output channel. Okay, the first weights will have total 16 outputs, so this is output channel. All right, now we have to initialize it. We are using the same initializer, whatever we have defined earlier. Okay, I'm going to create for the second convolution layer, and I'm going to change the name a little bit. Alright, coordinate size should be 2. 2. Alright, next I'm going to create the weights for dense layer. df dot, same process, get variable. I'm going to use float 32. We have to define the save. Alright, so our first dense network will have it's a bit complex calculations. What we can do, we'll have currently we have 24 rows, 24 columns, and after applying for the first max pool layer, it is going to have 14 by 14 14 rows and 14 columns. Okay, so I don't want to reduce this too much. Like I want to apply only one max pool layer, okay, not two max pool layer. So our final size of the dense input will have 14 rows, 14 columns, and total 32 channels. Okay, so let's use it dynamically. 32 channels, this many number of input we are going to have, and the output will have the dense layer size, that means total 64 neurons. So this is the same, and again we are going to use the same initializer. Alright, so here this 14 is coming. After applying two convolution layer, we are applying one max pool layers, so the image size will be reduced from 24 to 14. That's why we're using 14 by 14 image, and we will flatten that image, and then we are going to use the one-dimensional array as input to our dense layer. So that's why I'm using 14 into 14 by number of last convolution filters. We have one last thing pending to initialize, that is output bias, weights for the output layer. Okay, so let's follow the same process. Get variables, let's copy it. Okay, df dot float 32, name equal to wi out, shape equal to, let's define the shape as input will have this is the input, and output will have in class. Oops. And initializer will have the same. Okay, so I hope everything fine. Okay, all right, so in this particular cell we have defined the weights and biases, whatever we will require during our optimization process. All right, next step we are going to define the network. Okay, so let's name it. Okay, so this is the function we are going to define. I'm naming it as network. We're going to use, we have to pass the parameters like x for sure, y, okay, do you need y? I don't think we'll record y, but we are passing it. Okay, so let's see it. If not required, then we'll delete it. Weights, biases, strides equal to 1, the same for convolution layer, pool size equal to 2 for max pool layers. Then we have to define the dropout. Convolution dropout equal to, let's define here as 0.025%. Drop D equal to 0.25%. Alright, so 1, 2, 3, 4. I hope we have everything. If I have missed something, then I will come back and we'll readjust it. Okay, now first of all, before we apply the convolution layer on our data, we have to reformat the input. Currently we have one-dimensional array as input, so we have to make it in the form of the image, like 24 by 24 two-dimensional image. So I'm going to use the reshape function, which is provided by Tensorflow, to reformat the data. I'm going to give it a reshape. Okay, df dot reshape. Alright, so we have reshape function here. This is going to take x as input, and this is what going to have the output. Okay, it is dynamically take the input. This is 28 by 28 by channel last. Okay, so yeah, and the point is that TensorFlow is a language which takes channel as a last parameter. There are different languages like Theano that takes channel first. In that case, you have to define 1, 28 by 28. Alright, so I hope this will work fine. Okay, I'm sure it should work fine. Okay, conv1. This is our first convolution layer. Let's call our function conv2d, and we're going to use this x reshaped as input, and we need to pass weights, and we will pick up only one content from there. The next parameter will have the biases. Oops. Alright, so here we have passed the input x, w and b. X, w and b. So we have to specify the stride length as well, the input itself. Strides equal to stride. Alright, okay, so we are passing the strides. I think we are done with the convolution layer, first convolution layer. Next we are going to create the second convolution layer. In this case we are going to pass the first content from the first convolution layer as input, and weights and biases for the second convolution layer. So we are going to name it as conv2. So we are done with the convolution layer. This is a good time to apply the dropout as well. Okay, so let's apply the dropout. Conv2 equal to df dot neural network. I hope it is drop, no drop. Okay, we have dropout here. This is the input we're going to pass. Now in Keras you might be if you try to recall, we pass the exact value which is dropped during model training process. In TensorFlow, it takes the input as whatever being retained. So what we have to do, we have to use a particular function like 1 minus dropout to get the percentage of the retained input values, retained neurons basically. Okay, so our dropout is done. Next we are going to apply the max pooling layer, max pooling function. Okay, so here's the max pooling function, and we need to pass the first parameter as the previous layer and the pool size equal to 2. It's easy and simple. Now till this point we have two-dimensional array. We have a single record can contain multiple dimension basically. So what we have to do now, we have to reshape the content. So dense reshaped equal to df dot, let's call our reshape friend. We are going to take convolution 2D as input, and we need to specify the size. Okay, so these number of rows, it is going to be dynamic one, and so as I already discussed, the final output will have 24 by 24. This is not a very good practice. You should always try to avoid these hard coding, whatever I'm trying to do for this demo purpose, but don't write your code in this way. Number of convolution as input. Okay, so this many number of neurons will have. So at this point of time, we are able to create a single layer, one-dimensional array of size 14 into 14 into 32. Next, we have to create our dense layer, dense one equal to dense, and it is going to take input as, this is the input, and along with that it is going to take the weights and biases. Okay, let me copy this content. So D1 D1. We're going to apply the dropout layer as well after these dense layer, which is going to take a dropout as input, and dropout D is the dropout percentage. Next, we are going to have the final layer that is called output. It will have TF add, similar to whatever we have defined earlier, but we are not going to apply any activation functions in this particular case. TF dot metric multiplications of whatever content we are getting from here, from first dense layer, and our weights. W out, this one. So our net input is calculated here. So we have to add the biases as well. Okay, so we have multiplied the input values with the weights, and we have added the biases along with that, but we are not doing any kind of activations in this particular case, because that is something which we are going to do during our optimization process. And this particular neuron will return the output layer. Okay, I hope everything is fine. Perfect. The function has been created. Now so the final output, let's create another variable, output equal to, we're going to use this function now, and we have to pass all the parameters. Okay, x, y, I don't know why I'm passing y, but yeah, we don't need y in this particular case. Okay, you can try to avoid it. Okay, so all right, so let's redefine the function x, and we're going to have weights and biases, same thing whatever we have, weights and biases. Let's copy this whole content. Okay, so only I will change it to these two values. Oh, all right, let's call it. Okay, got some heat. Dimension must be equal. You have 16. All right, so we ended up in some issues. It is saying that it has some issues in layer 2, and it is saying that input shape of this and this. Okay, so let's see it. Layer 2, we have these weights and biases. This is the size, this is biases of size exactly whatever we need. Weight size of these, kernel says 3. All right, so the inputs in the weight size are not proper in this particular case, so it should be, number of channel is in this particular case is 16, so whatever output from our first convolution layer. Oops. All right, okay, it has already been initiated, so let me restart the kernel, and let me run everything. It will take some time, so bear with me first. What was it executed? Okay, so in this particular step, let me, I don't know, so many white space I have given. It's inconsistent and looking odd. All right. So next step, we are going to initialize all the variables. So this is another. We in TensorFlow we have to follow some standard, like we have to initiate all the variables. So we are going to create the initialization variables in this particular case. So that is init equal to df dot global variable initializer. So later we will call this particular initializer while creating the sessions. Next, we are going to create the cost function. Cost equal to, cost is something which we are going to optimize. We are going to use softmax categorical cross entropy function. Okay, and so I'm writing it down. Reduce mean. Okay, so TensorFlow neural network. I hope we have it. Softmax categorical cross entropy with logics. Okay. So here it will ask for two things. One is logics, that is the output whatever we are getting, and levels, that is y we have with the true classes. Okay, I hope it will work fine. Okay, it is saying it is correct. Now this is the optimizer. We are going to use gradient descent optimizer and with the learning rate whatever we have defined here. So let's create the optimizer, and it should be under training. Okay, it should be under train. Gradient. Alright, here is gradient descent optimizer. Learning rate equal to AR, whatever we have created above, and our target is to minimize the cost. Alright, okay. Now another variable we are going to create, that is for the accuracy measurement. Accuracy DL dot reduce mean. DL dot will cast it to float. It is going to be a bit complex. Dot equal. Okay. With an equal, we are going to use argmax function. Out of those 10 classes, whatever class will have the maximum argument, maximum values, we are going to have use with the axis equal to 1. df dot argmax, this is, will have y, x is equal to 1. Okay, this is equal, this is cast, it is going to be casted here. Okay, cast will end here and reduce will end here. Okay, good. Now the fun part. We are going to create the TensorFlow session and we are going to execute it. Let's make it. Alright, so first we have to create the TensorFlow session. TensorFlow session, as you can give any name to this session. I'm using session, which I normally do. First of all, oops, okay, so it has not been created yet. So we have to initialize all the variables we have created here. So we have to call this, we have to run this. Next, one important thing, we have to calculate the batch size. Batch size, we already have the number of batches it will require. Okay, so I'm creating a variable number of batches equal to integer. Create integer. Let's data dot train dot number of examples divided by batch. Alright, where is my batch size? What's wrong with it? Why are you not coming? Okay. Now we are going to execute the same set of data for the number of epochs whatever we have. For range epochs, number of epochs. For each epoch, we need to execute for each and every batch. For batch in range in batches. Now I'm going to take the X train and Y train for each batch. They have created a good function called next batch, and we can pass the batch size. So it will automatically pick up from the input data and it will assign those values to X train and Y train. Now what we are going to do, we are going to run the optimizer. Session.run. We have to pass it in some list. Later we can work with the cost as well. So let's copy the optimizer. Okay, so only here. So here we have two placeholder, right? If you remember that X and Y, those two things will be passed while executing this optimizer, and that would be passed in a form of fit dictionary. Fit dictionary equal to X, so capital X, yeah, it's X, and it will have X train and Y train. Alright, okay. So we are running that optimizer and we are passing these X train and Y train as to that placeholder. Okay, so few more things we have to do to keep track of the cost and basically the cost. Okay, let me create another variable here. It's something called, let's call it batch cost. Session.run. Here we are going to execute cost. This this function, and again we have to pass the same values. You can do it together here itself. You just have to pass this cost in this list, and you have to give this batch cost here. So I'm just creating it separate so that we can keep it in mind that this is something we tried. Along with that, to understand that our model is being trained properly, it's being trained that something is happening there too. We can add some of the verbosities, customized verbosities in better term. Batch, let's take every 200 batch, we want to print the current status. Okay, it was a big print, so let's add some simpler term there. Batch, you can pass this batch. Okay, now we'll add cost, this cost will come into picture, and you can add some accuracy also. Let's have some accuracy. Okay, you can format it in your own convenience, but what I'm going to do, I'm going to use another type of variable executions in TensorFlow, that is something called evaluation. Dot eval, and in this particular case we just have to pass the fit date directly. Okay, let's copy it from here. I hope it will work. Alright, so this is once done with this batch. For each batch, now once each epochs are done, we are going to have some validations accuracy. For example, print, the same thing will pass. Okay, I don't need from here. Okay, I will just adjust it a little bit. Epoch is epoch and accuracy is x test. Alright, so to add that validation accuracy, what we have to do, okay, I have some space here. So I'm going to call I'm going to load the test data as well. Okay, but I will use limited data. So I'm not going to use all 10,000 test record whatever we have. Then it will take a bit longer time and CPU as well. So what I'm going to do, I'm going to use little bit of higher values, maybe 512. Okay, so let me save it. Alright, so I think our model is ready. I can execute it for one epoch. Let's see it, whether it is working properly. Okay, so let's wait for some time. At least let's see it is working properly. It looks like it is working fine. With the default initialized value, we got accuracy of 18% approximately. Okay. It may take some time because I'm running it in CPU mode, and I already trained, I think, similar network earlier in GPU mode as well. So, but what I got after 20 epoch, I got accuracy of 98.5. So definitely it would require little more executions, little more additional epochs in that particular case. And so I'm just waiting for the first batch to come out, and right, in the meantime, what you can do, you can try to create these code by your own, and you can try to execute and train the model. And if you get any questions, you can definitely leave something in the comment portion. I will definitely personally clarify all those details, whatever, all those doubts, whatever you will have while training this model and while implementing this thing using TensorFlow. So here we can see after 200 batch, we got an accuracy of almost 90%. So this is not bad. This is going good. And this is a validation accuracy. All right. Okay. Good. You can play with this TensorFlow model, and you can try your own thing. A few innovations here and there, and definitely you will enjoy this neural network implementation using TensorFlow.